All right, thank you. This is a joint work with Encoder, who is with Google AI language. And in this talk, I'm going to focus on consistency of zero-shot neural machine translation. So this is the outline of my talk. And let me start with just a little bit motivating zero-shot translation and why do we care. So in the standard setup that we've seen so far, we have a pair of languages, let's say English and German, and we'd like to translate between the two. For each translation direction, we'd need to train a supervised model. And if the number of languages is, let's say, not 2, or it is n, we'd need n squared models. So to train a good bilingual model, we would need a lot of compute, as well as a lot of data. A lot of data for every single direction in this graph. So in practice, unfortunately, even if compute is not a problem, we still need to collect these data sets, and oftentimes we don't have access to that. And the reason is that the data is coming from the internet, and if we look at the distribution of the content, of the content over languages on the internet, we see that there is a lot of content in English and very few content in other languages. So it would be pretty challenging to collect these massive data sets for very low resource languages. But how do we go about solving this problem? So a more formal setup is on the slide. We're going to denote languages with nodes in the graph, and we're going to use denote translation directions as edges. The solid edges denote the supervised directions for which we do have data, and the dotted red edges denote the zero-shot directions. So our goal is to train the model only on the available supervised directions, while at the same time evaluate the performance on all directions. So we'd like to have a model that will be able to translate between all the directions at the same time, or equally well. All right, so how do we approach this problem? To understand how we can look at the components of the machine translation system, and the components are the data, the model, or the architecture, and the loss function. So previous work has tackled the first component, the data, and the approaches that leverage monolingual data, as well as back translation, as well as more recent methods, as the one was introduced in the previous talk. This is not the focus of this work. The other approach focuses on improving the model or the architecture, or basically the question, how can we change the model so that zero-shot performance can be improved? And a very simple approach was introduced by Johnson and others, where they use completely shared encoders and decoders. They share parameters of encoders and decoders, and with a simple trick of using language tags, they turn the standard machine translation model into a multilingual translation model that is capable of zero-shot translation. So let's look at the architecture. So they use the standard encoder decoder that technically doesn't need an introduction. It's a pretty famous model. The idea is that we get a source language, we encode it with some neural network, we get some contextualized representation, and then we decode by attending to this representation. So in order to make it multilingual, we're just going to append a tag that would indicate the target language we want to translate into. And now Encoder not only encodes the content of the sentence, but it also produces a representation that is suitable for decoding into the target language. So the decoder will figure out, based on this representation, which target language to translate into. So does this actually solve the zero-shot problem? Well, looking at the results on some public data sets from recent papers, we see that, well, the results are not zeros on zero-shot, on the zero-shot directions. There is some performance, but there is a discrepancy between the two. So the results are significantly worse than what can be achieved on the supervised directions. And if we cheat and actually add back the missing links in the graph and the data for these links, would see that the model would improve by 7 to 17 blue points. This is not just a single paper. There are other work that also evaluated their models on zero-shot translation directions. And the question is, how can we improve in general model in terms of the zero-shot performance? Do we need bigger models? Do we need more data? Do we need to train it longer? To answer this question, we introduced this notion of zero-shot consistency. And just to illustrate it, I'll use a sketch. So imagine that we have our neural machine translation with shared parameters, and we're training it over some number of iterations, and this is the supervised performance. And if we look at the zero-shot performance, typical curve that you would observe if you would train it on one of these data sets is that it first improves and then it sort of plateaus and saturates. Sometimes it decreases, and from run to run, actually the fluctuation would be pretty drastic. It could be a few blue points. So we have this gap that sort of grows over time. And what we actually want to have a consistent model that is trained on the supervised data, but at the same time, the zero-shot performance consistently sort of improves over time, over the iterations. And basically, we would like to be able to control the gap. So we define zero-shot consistency as follows. This is the bound on the loss on the supervised directions, right? And we would like our model to be able to have also bound the loss on the zero-shot directions. Basically, if the loss is bounded on the supervised directions, it should imply that it is somehow bounded on the zero-shot directions. And importantly, when the model is perfect on the supervised directions, we want it also to be perfect on the zero-shot directions. All right, so there are methods that are actually satisfy this definition and are provably zero-shot consistent. So one of them is super simple. It's bridging through a pivot language. Basically, we assume that we have some language that is central in our graph, and we would be able to get supervised models, let's say in this case from German to English and from English to French. And whenever we want to translate from German to French, we just pipeline the models together. So this is a go-to approach and a very strong baseline, and we show in the paper that is actually zero-shot consistent. The disadvantage of the approach is that first it's a pipeline. The errors may accumulate. It very much depends on the quality of these supervised directions, but at the same time, it will also be pretty expensive to evaluate, to use at inference time because we need to run the model twice. So another approach is distillation, also introduced in previous work, and the idea is that to basically generate some synthetic data and distill a zero-shot model using this synthetic data. Again, this approach is also zero-shot consistent, and the only disadvantage is that for every single zero-shot direction, we would need to go and distill parameters of a new model, and this might be challenging. Also, distillation, if all the parameters are shared, distillation might affect the other directions. All right, so we propose in this work agreement-based learning for multilingual NMT that would actually result in a fully consistent model. And the basis of our approach is actually tackling the third component of the machine translation system, which is the loss function that we're optimizing. Okay. So again, the setup, the standard loss that was used by Johnson and others is pretty well known in statistics literature, and it's called composite likelihood. And it's called composite likelihood because we just take independently losses on all the supervised directions, just stitch them together through a sum, and just optimize the resulting loss. It has some nice properties, but unfortunately has no statistical guarantees for the performance on these zero-shot directions. Basically, if you optimize this loss at a local optimum, the performance on these directions could be pretty much random. So what we propose, let's just take a look at an example to see how we can improve upon that. So again, we're trying to translate between English and French, and here we have two loss components, one for translating from English to French, and the other one is from French to English. We know that in our graph, or the setup, we do have not only these two languages, but also, let's say, German and other languages. So we can introduce a latent variable, or a latent translation, and make this equivalent transformation. So these latent translations that we introduced in each of the models are, in fact, independent. So we didn't change the loss at all. But what we propose to make them dependent, and in fact, time them together. Right? And the resulting loss that we call agreement-based loss ties these latent translations together. After a bit of rewriting, we can actually show that this is, in fact, this loss is actually equal to the standard composite likelihood plus some additional term, which is called the agreement-based term. So how are we going to train the model in this regime with this new loss? Well, basically, for every sentence that we have in our parallel corpora that are available to us, we're going to, in addition, try to translate, let's say, from English to German and from French to German, and try to match these translations via this loss. So in the paper, we show that, in fact, agreement-based learning, by optimizing this loss, will get a zero-shot consistent model that will be consistent across all the directions at the same time. Right. So the only thing that is missing is how are we going to go about computing this term, because this is a sum over all possible latent translations, which is pretty much intractable. So we have to make some approximations. The approximations that we make are fairly straightforward. So one of them is the Jensen's inequality. So we'll lower bound this term. The other one is that we have to subsample one of the which latent language we're going to try to enforce agreement to. This is important in the case when we have a lot of languages in the system. So this would reduce the complexity by a factor of the number of languages. And finally, we use a greedy continuous decoder in order to be able to compute and backpropagate the gradients through this loss. I don't have time to go into the details of the decoder, but you're welcome to look it up in the paper. All right, so this is the computation graph. Again, so the only thing that we need to do is to encode both source and target languages as if we were translating them into this auxiliary latent language, and then basically decode them into that language and then try to match them through this agreement-based loss, approximate agreement-based loss. Again, all the details are available in the code and in the paper, but the key point here is that it's only a constant factor in terms of computation time overhead that we introduce by adding this additional loss. So there are 2 extra encoder passes, there are 2 extra greedy decoder passes, and there are 2 extra teacher-forced decoder passes. Okay? All right, so finally, I've introduced this framework. Now I'd like to discuss some results and our experimental evaluation. So to evaluate all these methods, we've considered the following data sets based on UN corpus and on Europarl. These data sets are based on some formal language. The number of languages was 3 or 4. The number of parallel sentences were about 1 million per supervised direction. And we also ensured that the parallel data was cleaned. So there were no multi-parallel identical sentences in the data set. These data sets were used in the previous work. We used 2 more zero-shot translation tasks. One of them was introduced pretty recently and was a competition and was actually focused on zero-shot machine translation. So what we noticed is that there were a lot of multi-parallel sentences, unfortunately, and we argue that actually this data set is perhaps not the best benchmark for the task. So we actually cleaned it and introduced this IWSLT17 star that removes most of the, or pretty much all of the multi-parallel data. All right, so these are the results on the UN Corpus 2. I'm going to show you just some selected number of the results. For the full set of results, you can refer to the paper. So what we see here is that by introducing agreement-based objective, we're able to not only improve on the zero-shot directions, but also we don't lose in performance on the supervised directions. So the model pretty much matches the baseline. And on all these, almost all the zero-shot directions, we either on par or superior to the pivoting baseline, which is one of the strongest baselines. Now, on the IWSLT data set, we observe that on the original data set, there is something interesting on this zero-shot performance, and this is just average zero-shot performance across 4 zero-shot directions. So the original data set, as I mentioned, contains a lot of multi-parallel data, and because of that, the performance of the zero-shot models are quite inconsistent in the sense that certain directions are even better than the supervised directions, which was reported in the previous literature. So after looking at this result, we decided that we need to improve the data set. And after cleaning the data, we had to remove about 50% of the sentences from every single parallel direction. We had to also reduce the number of supervised directions. And now the pattern that we see, the difference between the supervised and zero-shot directions is more consistent. So we see there is actually significant gap. All right. Finally, we performed some experiments on the limited parallel data. And these are plots for the Europarl data set. Basically, we limited the number of parallel sentences, supervised parallel sentences, to a few thousands, up to a half of the data set. The full data set was 1 million per supervised direction. And what we see, the first observation is that we see a consistent pattern of improved zero-shot performance as we increase the amount of data. But also we see that pivoting is quite sensitive to the language pair that we're looking at because it's quite sensitive to the supervised direction. So sometimes it is superior to the agreement-based model, or sometimes it is inferior. So it oscillates across the data sets, while agreement is pretty much stable. All right, in summary, and to conclude, we've introduced 3 components in this work. First, the notion of zero-shot consistency. Then we proposed the agreement-based learning that satisfies this notion. We also analyzed other methods available in the literature. And finally, we've introduced a pretty much reproducible experimental setup that can be used with public data sets. And we've improved one of the data sets, as we believe. Finally, this framework is applicable beyond multilingual MT, or pretty much to any zero-shot performance. It's just a machine learning framework. All right, thank you.
Questions? I'll ask a quick one then. So it's interesting that cleaning the data was really important. And I wonder to what degree the original direction of translation matters in the data. Whether the data was original English and translated into French and things like that. Did you notice any effects in your experiments?
So if I understand the question correctly, is the original data, so does it matter which directions we clean, or? Yeah,
so if the data was originally in English and then translating out of English to a bunch of different languages, does translating from translationese into original English and then into the translation, is that easier than translating along the real translation direction?
So we actually didn't do that, so we didn't generate the synthetic data. What we did for cleaning the data sets is basically we looked at exact matches between the sentences along different directions, and we looked at basically triplets. So let's say there is a French, English, and German. So we looked whether there's an overlap within the English between the corpora between English and German and between English and French. And if there is an overlap, we just, half of the overlap let it be just in one of the data sets, and just the other half of the overlap we'll keep it in the other data set. So there was no synthetic data that we generated. But we randomized the process, and there was no significant difference between how you randomly split the sentences.
All right, there are no further